Welcome to FMA 0134 Mathematics 3, Chapter 5 Hyperbolic Function. In this video, we're going to look at the identities of a hyperbolic function. Okay, they are at the beginning, before you want to prove others' identity of a hyperbolic function, then at the beginning of it, we try to show how to find the set of identities for the hyperbolic function. There are two different ways to show it. The first one is the one inside your module. By using the definition of hyperbolic function, which is defined in exponential form. Okay, then the second one, which is not inside your module, which is using the Osborne rules. Okay. So now let us look at the first one. Is the one using the definition of hyperbolic function in the exponential form. So the first one, actually the number one, cos x plus sine x equals to ex. This one we already show at the beginning of the actually in the first video, but that doesn't matter. So what we how you want to show this one? Basically, we are using the definition of our cos x actually is ex minus e minus x over 2. Then we have our sine x actually is ex plus e minus x over 2. So when we have a cos x plus sine x, so we use the equation 1, sum this equation 2, so we're going to have a ex. Okay, so contrarily for the cos x minus sine x, so we use the equation 1 minus the equation 2, so we get going to have a e minus x. Okay, so by using this one, so the first one they ask us to show cos squared x minus sine squared x. Okay, if for the student who are quite confused how you want to link this one, the over here the our star A and the star B, how you want to use our star A and star B to link to the equation A. Okay, so what I want to introduce here is, do you remember when we have our A square minus B square? Okay, a square minus b square is by the we can separate it into a plus b, a minus b. Okay, so over here our a actually is cos x, so we're going to have our cos square x minus sine square x actually is cos x plus sine x, because a is cos, the b is sine, so I have a cos x minus sin x. Okay, so then what is cos x plus sin x? From our star A, actually this one is ex, and then multiply with our second one, cos x minus sin x is from the star 2, so is the e minus x, and we have by using the algebraic what we know that is for the index pm multiplied pn actually is pm plus n, so we have our ex plus minus x, so we have our e0 actually is 1, so we already showed our right hand side. Okay, so this is the first way that how you use the definition. Actually the basic definition is from our number 1 and number 2. Then we lead to the star A, star 1 and the star 2. Okay, now the second one also, this one they give you a clue that is using what we have from the star 1, cos x plus sine x equals to ex. Cos x minus sine x actually is just now our star 2, so this is our star 1, this is our star 2, and considering our and then they ask you to considering the cos x plus sine x squared plus cos squared minus sine squared 2, and then they ask you to show this one. Okay, so before we want to show this one, so what we do is we take this one, cos x plus sine x squared plus cos x minus sin x squared. And we can see from this equation, okay, this equation, I name it as a star tree. From this star tree, we don't see any relationship. We couldn't see is not in this form for our b. So what we can do is, okay, so what we try to do is, so we try to expand our star tree. Okay, so we're going to have a cos x. Okay, still remember a plus b squared actually is a squared plus b squared plus 2ab. Okay, plus 2ab, sorry. Okay, then the a minus b actually is cos a, cos squared a squared plus b squared minus 2ab. Okay, from here, both of it, this one can cancel off. So I have my cos squared. So I have a 2 cos squared x actually is plus 2 sine squared x. Okay, then over here, the left-hand side of this one expansion is already done. So now we explore from here. Okay, what we do is we explore from here. Okay, we explore from here, but we use the definition of our cos x plus sine x for the ex. So I'm going to have my ex. Okay, cos x plus sine x actually is ex square plus this is cos squared minus sine x actually is e minus x squared. So when you expand it, so you will have e2x plus e minus 2x. So that's mean if you use the expansion, okay, so the expansion of cos x plus sine x squared on the left hand side is this one. While on the right hand side actually is e2x plus e minus 2x. Okay, so if you see here, okay, now actually this one actually is our left hand side. So what we do is we don't want the 2, we throw it to the other side. So I have my cos squared 2x plus sine squared 2x, okay, equals to half e2x plus e minus 2x. Okay, so actually what is this? If you see that is, if you replace the 2x with a, okay, so that means actually the right hand side actually is your cos a. Okay, while my a actually is 2x is cos 2x. So I have already proven my b. Okay, so this is the way that how you try to prove the cos squared x plus sine squared x equals to cos 2x. Okay, and then over here they are having the same thing. Okay, but now they are saying they're having the same thing. They ask you to show, okay, there is a little difference. This one is a plus, this one is a minus. Okay, so means that we are doing the same way. Okay, we are doing the same way. So over here we're going to have okay, so now actually the cos x I write as a chx, then our sine x shin x I write it as x. So over here if I expand the left hand side of this one, I'm going to have a chx square plus sh square x plus 2chsh, okay, x, and then minus, okay, because this is a minus, so I have my ch square x plus sh square x minus 2chx shx. Okay, this is my left hand side of this one. So what I do is then after that, like the previous slide, so what we do is we expand it. So when you expand the negative, these all are cancel, so you only have a 4 chshx and equals to this one. If I substitute the definition from the star 1 and the star 2, this one actually is my ex e2x minus e minus 2x. So this one I'm going to have a e2x minus e minus 2x. As we know that like the previous one, I need the 2 because I need to bring down here. So ECHX, HHX actually is 1 over 2 e2x minus e minus 2x, and the right hand side actually is our sine 2x, and this is the 2 sine x cos x. Okay, so we already proven the C. So basically, this the first method is you try to relate the sine, okay, the cos x and sine x equals to ex, and then we combine with some the common algebra manipulation, so then we can get our proven. Okay, then over here, please check the example 5.3 in your page 134 in your module Mat 3. So this is the questions. Okay, why this one over here? Because this one, they ask you to show this one, so you can have a look in your module. Okay, so this one you're going to explain in our class. Okay, same thing. Okay, then the second one, we call it as an Usborne, okay, Usborne rules, okay. The Usborne rules, they said that is this is a lot easier method, which is we are not using the definition of exponential. So what we do is, it said that trigonometric formula can be converted into the formula for hyperbolic function, okay, which you convert the cos x. Whenever you see the cos x, then you just change it to become cos hyperbolic x. And when you see the single sine x, you change it to be single as a sin x, except you have a product of two. Okay, for example, if you see this one, okay, and what when you see like sine squared, okay, okay, so for example, you say that when you see cos, okay, the normal formula we have from the trigonometry is cos 2x equals to 1 minus 2 sine squared x. So the cos 2x, what you do is, whenever you see the cos, you just change it to be cos2x. And but the thing is, now this sine actually is a product of a two sine, okay, so it means that is after you change it to become sine sin square x, what you need to do is, if you have a minus, you must change it to be a plus. If the original is a plus, you need to change it to become a minus. So for example, cos 2x, also we have another two formula. The first one is 2 cos squared x minus 1. So when you want to change it to hyperbola, so hyperbolic, so cos just change it to the COHH, and the cos just change it to COHH. There is no changes of sign for the plus minus for the cos, okay, but only have the change for the sine square. Okay, so then we have another formula, actually is a sine 2 is the cos 2x, actually is 1 minus is a okay, sorry, actually is a cos square x minus sine square x. So when you want to change to hyperbolic, so cos never change, then this cos is going to change it to be, and this change it, but since this is a minus, we change it to become a plus. Okay, so this one is a lot easier, but the problem here is, please be careful, because if we have a sign, very easy you can detect is a sign. But how about when if involving tangent, and then we are involving cosecant? Okay, so now, let us look at another few examples. Okay, so given the first one is sine 3a equals to 2 sine a minus 4 sine cube a. Okay, so now remember that this is not because of if you odd not the odd power, then you no need to change the sign. Then the even power you need to change. No, over here that is the statement of the Usborne means is, if you have a two multiply of the sign, then you need to change the sign. And the sine cube actually is by the sine squared A multiplied by sine A. And this is a negative 4. So these two is going to make it to change the sign. So this one is become a plus 4 sine hyperbolic A. Although it is a power of 3, but because it is the form by a power of 2 and power of 1, so because of the power of 2, you need to change the sign of that this one from a minus, change it to become a plus. So now, so we're going to have sin 3a equals to 2 sin a minus, plus 4 sin power of 3a. Okay, so this is how, when you have a power of 3. Okay, now after that, let us look at the most basic we have. We always say that sine squared plus cos squared x, sine squared theta plus a cos squared theta equals to 1. So what we know that is this one is going to change the sign. So minus sin squared theta plus cos squared theta equals to 1. But normally, we seldom want to put the negative in front. So then we have another identity. This is a cos squared theta minus sin squared theta equals to 1. Then, as I said just now, when you have a tangent, you need to be careful because tangent is formed by the sine, okay, sine squared theta over cos squared theta. So then you become your tangent squared. Okay, the secant actually is 1 over cos squared theta equals to 1. So you no need to be worried about cos. We only need to worry about the sine. So because this is a sine squared, then this sign is going to change it to be minus. So what we can do is, so it's a secant squared theta equals to 1 minus tangent hyperbolic squared theta. Okay, so this is how you're going to be using the Usborne rules to change from a trigonometry formula to become a hyperbolic function. But one thing that, as I said, that is, although this method is a lot easier compared to the first method, but the thing is you need to be very careful whenever you see tangent, the sine squared and so on, because it is involving the change of the sign. Okay, the sign here means is the sign positive and negative. Okay, so then we have this one, then we can and over this example, this one is using the identity of a trigonometry function, but in your book, you're going to have using another method, which is in your page 137. Okay, and then over here, we have a list of the formula, okay, for the hyperbolic function. Okay, from this formula, okay, if unless the question asks you to show that number 1, okay, by using a whatever method, okay, doesn't matter. So then maybe you can use the proving by using the exponential definition. If not, then these formula are ready to be used. Okay, so thank